So let us continue with our study of the Fokker-Planck equation, and for the next lecture or two we are going to talk about a physical model of particle in a fluid undergoing random kicks due to the molecular collisions, and at the same time possibly be subject to some external force. But let us look at the case first where you just have free diffusion of a particle in a fluid. I will not specify at the moment how big this particle has to be. We will come a little later and distinguish between different time scales, and we will see under what conditions this whole thing applies. But right now we take a very naive approach and say, alright, suppose I have a small particle inside a fluid and this is undergoing collisions, random collisions due to the agitation, thermal agitation of the molecules of the fluid. What kind of equation of motion can we write for this system here? Recall that we made a correspondence, we stated that there was a correspondence between certain kinds of stochastic differential equations describing diffusion processes and the corresponding Fokker-Planck equation. So what I am about to do now is a physical example of that in a very simple case in which the drift term will be a linear in the variable. So let us look at this in a little bit of detail. Again, to refresh your memory, I said that if you had a stochastic equation in some random variable x, I use the symbol x, but now for this application I am going to use x for the Cartesian coordinate of the particle. So let us be neutral and call it xi or something like that. So if you have a stochastic equation of the form xi dot equal to sum f of xi plus g of xi times the white noise, and this was white noise Gaussian white noise in fact, satisfying eta equal to 0 and the autocorrelation T eta of T prime equal to delta of T minus T prime. Under those conditions this was equivalent to a Fokker-Planck equation for the conditional density of this xi with some initial condition of the form delta over delta t p of xi t for a given xi naught, say this is equal to minus delta over delta xi f of xi times p plus 1/2 delta 2 over delta xi to g squared of xi times p. This was the Fokker-Planck equation, whereas that was the stochastic differential equation for this random variable xi. Now let us look at the simplest example. We even wrote this down. I said if the position of a particle undergoing diffusion on a line satisfies x dot equal to square root of 2d times eta of t, this immediately implied that p of x comma t with some initial point x naught satisfies the diffusion equation delta p over delta t equal to d2p over dx2. That was the correspondence we had made. But now let us be a little more detailed and ask, look, whatever force the particle is subject to is going to cause an acceleration. So let us say that the equation of motion that you should write down for this particle moving in one dimension or one Cartesian coordinate of it, let us call the velocity v, and we should really say, well, mb dot, that is the acceleration, should be equal to whatever force it is subject to. And in the simplest instance you would say this force is a completely random force. It is due to all these molecular collisions, I do not know anything about it. So in the simplest instance you would say this is equal to eta of t itself in this fashion. But of course dimensional reasons and as well as the fact that this eta of t need not have unit delta function strength but some arbitrary number. So let us call it equal to square root of some gamma times eta of t, where this is some constant which we may or may not be able to determine in a self consistent way to start with. Okay. Now what does this imply? This immediately implies a Fokker-Planck equation for the quantity of interest, namely the velocity distribution function, density function. But instead of writing this down, let us take this stochastic equation seriously and ask whether it makes any physical sense or not before we do this. Now this will of course mean V dot is this, and you can formally solve this equation. This is a stochastic differential equation, but it is very, very simple, and we can formally, in principle, we can solve it. So this will of course immediately imply that V of t equal to some initial condition, whatever it be, some initial value V naught, plus square root of gamma over m integral from 0 to t dt prime eta of t prime. Okay. Now remember our physical context, we have a fluid, we imagine a fluid in which we are looking at one Cartesian component of the velocity of some tagged particle, and this fluid is taken to be at thermal equilibrium at some temperature T. Okay. Then it says the velocity is equal to this, the instantaneous velocity, but what we are interested in is averages always. So what is the average value of V of t? Now when I say averages, I got to be a little careful. Average over what ensemble? We have already specified an initial condition. So it is an average over all those particles whose initial value of the velocity is given to be some number V0, right. It is not an average over all possible initial velocities as well, that will come a little later. So we have two classes of averages, one is over a sub collection of particles whose initial velocity is V0, and then we say look, let us average over V0 as well over some initial distribution, or since I said already that the fluid is in thermal equilibrium at temperature T, over say the Maxwellian distribution at temperature T. That is what I should do really. So to distinguish between these two things, these two kinds of averages, let me put an overhead bar to denote averages over a given initial condition V0, right, and then a subsequent average over these V0s will give me a final average for which I will use angular brackets. So this will immediately imply that V of t bar is equal to, well, average of V0, but V0 is a deterministic given number of course, V0 plus the average of this integral, but the integral is essentially a summation over different values of eta of t prime. So since two different sums commute in either order, this overhead bar is the same as putting it inside the integral, right. So this becomes plus square root of gamma over m integral 0 to t dt prime eta of t prime, an average over all realizations of this eta of t prime. Now the physical assumption is that you are looking at one particle that is with a small number of degrees of freedom inside a huge collection of particles in thermal equilibrium, and the heat bath which is providing the fluctuations of the velocity of this particle, that is not going to be affected by what this particle does. So whether I fix the initial velocity of the particle or not is not going to affect the average value of the random force at all. So as far as eta is concerned, whether I put a bar or take a full average, it does not matter at all. We have already assumed that it has got 0 average, it is a Gaussian white noise, so this quantity is actually 0, this integral, and this becomes equal to V0, since the average value of this random force is 0 in any case. Okay. So far so good. It just says the average value remains this, which is physically expected. You are saying that the force can be as much acts as much to the right as to the left. On the average, the velocity component is 0, the average is 0, it remains whatever it was initially. But what does this tell you? What is V squared of t tell you? If you compute the square of the velocity, then I have to find the square of this guy and find the average. So it is evident that there is a term which is V0 squared, and then there is twice V0 times this, and then I want to take an average. So let us put that average in there, there is nothing to average here, and then I have V0 times eta of t prime averaged, but V0 comes out of the averaging and it is just the average of eta of t prime again. So the cross terms average again goes to 0, but then I have a term which is plus gamma over m squared when I square this term here, and then I have to take 0 to t dt, let us call it dt1 so that I do not mess around with primes, and then again 0 to t dt2 eta of t1 eta of t2 with an average out there. Okay. But that quantity is not the product of averages because eta is a random variable with the delta correlation, this kind. So I have to put that delta correlation there, and then it says that v squared of t average is v naught squared plus gamma over m squared, an integral over this with delta function. Did I put the, yes, a delta of t1 minus t2 in here, okay, and that contributes as long as t1 equal to t2, and that always contributes for all values of t1 between 0 and t, and that is easy to see because if you draw a little picture, here is t1, here is t2, and in each case you are going to integrate from 0 to t in this fashion, and the delta function constraint tells you t1 equal to t2 out there. So it says if you do the t2 integration first, which is the way I have written it here, then it is clear that no matter what t1 I have between 0 and t, there is a value of t2 as you scan this at which the delta function fires. So I can therefore remove the t2 integral and replace wherever t2 appears, I replace it with t1, okay, and that gives you 0 to t dt1, and this integral is gone, the t2 integration is gone, okay, which therefore gives v naught squared plus gamma t over m squared. So it gives us this rather unphysical result which says that the square of the average value of the square of the velocity increases without bound as t increases, okay. If you identify the temperature with half m v squared average, this means that if you leave this particle untouched, you keep a beaker of fluid, then the average kinetic energy of any particle in there increases without bound, okay, and the effective temperature increases without bound. So it is completely unphysical, complete. So this cannot be right, this model cannot be right, this equation cannot be right because there is nothing else that has can go wrong here, okay. You might say, oh, perhaps this is unphysical, perhaps this is not correct, I should not use a delta correlation, I should use an exponentially decaying correlation with some finite correlation time. But even if you did that, you would still get an unphysical answer, and I leave you to check this out. Even if I took this quantity to be some e to the minus t over tau for some very small value of tau and computed what this number is explicitly, you would still get an unpleasant answer here. It would still be unphysical, and this is not right. So the only thing that can possibly be incorrect would be the initial model itself. This model cannot be right, okay. And what have I left out of it? I have left out the fact that there is a systematic component in the random force. This force eta is completely random, uncorrelated and so on, that is fine. But however, if this stacked particle starts moving in one direction at a velocity higher than the average velocity, it gets hit back by the friction in the problem, by the viscosity. The very same molecules that cause fluctuations in its velocity will also damp out these fluctuations by having more collisions from the front than from the back if you are moving in this direction, okay. So this means that I have to modify this model, and this is not correct. Let us see what the correct model is. The correct model would be mv dot equal to, there is an eta of t, so there is square root of gamma times eta of t, that part certainly exists, that was the original model. But there is a portion which says there is a viscous damping, and for small velocities Newton's law of viscosity tells you the viscous drag is proportional to the force but with an opposite sign, right. So this is equal to minus m gamma v plus this, but gamma is a quantity which has dimensions of 1 over time, so that it matches this on this side. It is a friction coefficient. I took out the m explicitly because it is easier that way, right. So this is my model. This is, by the way, the simplest example of what is called a Langevin equation. But this is again Gaussian white noise, but there is a systematic component to the random force. A model, again it is a model, and we have to see whether it makes any physical sense or not. Now look at what is going to happen. We repeat exactly what we did before. When I divide through by m, then average V of t equal to the solution. Now, by the way, we can write down the solution first, let us do that. So the solution is V of t equal to V naught, but that is multiplied by e to the minus gamma t, because there is this term here, plus square root of gamma over m integral from 0 to t dt prime e to the minus gamma t minus t prime eta of t prime. Because this is of the form dy over dx plus p of x times y equal to q of x, and you have the standard formula for solving a first order differential equation of that kind, an inhomogeneous equation, and this gives you the explicit solution. This here. That is already telling us we are on the right track, because it immediately tells us that V of t average is V naught e to the minus gamma t, because whether this factor is present or not, when you take the average of eta, it is again 0. So you have this feature here, already getting us on the right track, because it says that if t becomes very large compared to gamma inverse, this says the average velocity goes to 0, which is exactly what you would expect. There is no reason why the memory of the initial condition should remain forever. When you have viscosity in the system, it is going to be damped out. So this is a good feature, that it exponentially vanishes as t increases. Okay. And what does the square do? It does exactly what happened earlier, except for that extra factor. So this is now V naught squared e to the minus twice gamma t, because that factor remains, plus gamma over m squared, once again integral 0 to t dt1, 0 to t dt2, e to the minus gamma t minus t1, e to the minus gamma t minus t2, and then an eta of t1, eta of t2, whose correlation average value is delta of t1 minus t2. Okay. Exactly the same way as before, we can now do the t2 integration and replace t2 with t1 everywhere. So this integral is easy to do. It is V naught squared e to the minus 2 gamma t plus gamma over m squared integral 0 to t dt1, and then there was already an e to the minus 2 gamma t sitting here, and then you had e to the gamma t1, e to the gamma t2, but now t2 is equal to t1, right. So e to the 2 gamma t1, and that is the integral, right. E to the 2 gamma t comes out of the integration, and then you have to do this fellow here. So this is V naught squared e to the minus 2 gamma t plus gamma over 2 m squared gamma, because when I do this integration that factor comes out downstairs, and then e to the 2 gamma t1 from 0 to t here. The first term will cancel out and give you a 1, and the second one gives you e to the minus 2 gamma t. Because this integration is e to the 2 gamma t1 minus gamma t minus 1. So that is the result out here, and this has no exponential blow up. this linear blow up. This does not increase unboundedly as t goes along because the exponential factors cancel and go to 0, and it looks like it is going to some constant, which is what you should expect, because if you are in thermal equilibrium it should remain fixed in thermal equilibrium, right. You could also rewrite this as equal to gamma over 2m squared gamma plus V naught squared minus gamma over 2m squared gamma e to the minus 2 gamma. Okay. This is for a given V0. For some over the sub ensemble of particles with a given V0, this is what you get. And now what happens to it as t tends to infinity? Well, gamma t tends to infinity, this becomes gamma. Independent of the initial condition, it has forgotten the initial condition and it tends to some fixed limit. Okay. So remember that this average is being taken over a conditional density, the condition being that the initial condition is V0. So it is being taken, really that average is being taken over this P of Vt given a V0, this thing is given to you. We have not yet found this, we have not yet even written down the Fokker-Planck equation for this process, but already it is telling us that the mean square value has this structure, better have this structure here from the Langevin equation itself. Okay. And now if you insist that in equilibrium this whole thing is independent of time as t tends to infinity, now if you insist that this should be true at all instants of time because this fellow here is in thermal equilibrium, another way of saying it is let us compute what V squared average is over a full average. So I compute V squared of t, and what can that be? How do I compute it from V squared bar of t? I should now average over all V naughts, right? Over what ensemble should I average this? It is in thermal equilibrium, so over the Maxwell distribution, right? So I need to compute V squared of t equal to integral V squared of t bar over P of V naught, V naught, where this thing here is the equilibrium or stationary distribution, and that is of course m over 2 pi k Boltzmann t to the power half e to the minus mv squared over 2 k Boltzmann t in V naught. So I have to do the average over this distribution, right, and then I get V squared average here. Let us do that and look at what happens. This is equal to, well, this follows a number, there is nothing to average, and P of V naught is a normalized distribution. So you are back with this has got to be as it is. So this is equal to gamma over 2 m squared gamma plus this quantity is averaged over, you need to average over this definitely, but what is the value of V naught squared average over the Maxwell distribution? But the average kinetic energy is half kT, it is only 1 degree of freedom. That is just the Gaussian, once you put that in and do a Gaussian integral, you discover that the half mV naught squared average is equal to half kT, right. So V naught squared average is kT over m. So this immediately tells us this is k Boltzmann t over m minus gamma over 2 m squared gamma e to the minus 2 gamma. But this cannot depend on time. The system is in thermal equilibrium, right? It can't depend on time. And the only way that can happen is if this is equal to that, right? So if this is equal to that, if gamma is such that this quantity is equal to that, the time dependence goes away because the system is in equilibrium. At no time does half mv squared average change. It remains kT over m because the system is in thermal equilibrium. Right? And that is completely consistent with the fact that if this goes away, you get exactly kT over m here once again. You need that because if this constant had been different from that constant, you are in trouble. The fact that you insist that this should be equal to that automatically gives the right value here also. So it says that consistency requires we must have gamma over 2m squared gamma equal to k Boltzmann T over m, or capital gamma equal to 2m little gamma k Boltzmann T. This is required by consistency. Now what does it mean physically? Well, if you go back to the Langevin equation, that equation was V dot equal to gamma V with a minus sign equal to minus gamma V plus square root of gamma over m eta of t. Okay. Now this measured the viscous damping in the medium, the viscosity in the medium which damped out fluctuations. This measured the strength of these fluctuations. How far does it get pushed out in some sense? How strongly does it get kicked? And now we are saying that the two are not independent parameters. The larger the viscosity, the larger the fluctuations here, or conversely the larger the fluctuations, the larger the viscosity must be to damp out those fluctuations and maintain thermal equilibrium. Okay. There is therefore a connection between the source of fluctuations and the dissipation in the system. Okay. And this is the first example of it, the simplest example of it. It is called the fluctuation dissipation relation or theorem, if you like, in some case. We will come across more further examples of this, but this is the simplest of the lot. Okay. You are already familiar with this in the context of thermal noise in a resistor, electrical resistor. You know, if you have an electrical resistor, due to the Brownian motion of the electrons in it, voltages are set up at the two ends and there is a current which fluctuates and flows in this resistor. And this current, you can ask, this fluctuating current, what is the power spectrum of this fluctuating current? How much is the power carried by it in some given frequency window? Okay, we will talk about power spectra of noise a little later, but we know that there is a relationship which connects the dissipation in the resistor measured by the resistance to this the temperature on the right hand side. So we know that the power spectrum of the fluctuations in the response of the system is related to the resistance multiplied by the temperature, this one, and it is called the Nyquist relation. This is the Nyquist relation in this context. It is exactly the Nyquist relation for thermal noise or Johnson noise or whatever. Okay. But physically what it means is the same fluctuations that give rise to oscillations or which give rise to randomness in the velocity are the ones also responsible for the dissipation in the system, and there is a consistency condition between the two. You can't have one unboundedly growing without independent of the other in this context. It is required for thermal equilibrium. This is required to maintain thermal equilibrium. So we will put that in henceforth, and now notice that once you put it in, this thing here becomes equal to kBt over m independent of t. So it is already starting to tell us that perhaps this V of t is really going to be a stationary Markov process. We started with that assumption, we already put that in, I have not explicitly shown it here, but we already, when we wrote this Langevin equation, to cut a long story short, once you have a Langevin equation of this kind, then what it means is, if this is a Gaussian white noise, in other words it is a stationary Gaussian delta correlated Markov process, then you are guaranteed that this V, the output or driven variable, is going to be a stationary Gaussian Markov process, but not delta correlated. It will have a finite correlation time. What do you think will be the correlation time of this velocity? Or what time scale is this thing losing its, or what time scale is this average value going to 0? It is going e to the minus gamma t. So there is only one such time scale in the problem, which is little gamma inverse. Gamma. So indeed it will turn out little gamma inverse is the velocity correlation time. With that information there which we have got there, we can actually write down the solution completely to the Fokker-Planck equation fully, but we will not quite do that as yet. We will just see what the Fokker-Planck equation is before we do this, but we are going to use this connection henceforth. Now let us write that Fokker-Planck equation down immediately using this correspondence between the Langevin equation and the Fokker-Planck equation. We write it down, then look at what its solution is, but in the meantime we will compute the velocity autocorrelation function. So now that we know what this little gamma is, this is equal to minus gamma v plus this fellow is 2m little gamma kt. With a square root over m, so let us take that over m. That is the Langevin equation, where we put in this consistency condition. Okay. And what does that imply at once? It at once implies that delta over delta t, p of v comma t, v naught, must satisfy, the drift term is this, but remember by looking at our general rule here, it is minus, so the minus cancels, gamma is a constant, delta over delta p, v times p, the same p, plus 1/2 the square of this guy, in the half this kills that, so you have gamma k Boltzmann t over m d2p over delta v2. Okay. This was the original Fokker-Planck equation, the first one written down. Okay. We use that term in general for the second order master equation with up to second derivative, but this was the original one with a linear drift term out here. Okay. Now of course you can take this equation and ask what is its solution, but we need the initial condition, and that is obvious here. The initial condition is p of vt v naught equal to delta of v minus v naught. This is the initial condition, of course. What is the stationary distribution? Is there a stationary distribution in this problem? Unlike the diffusion equation where everything went to 0, the question is there a stationary distribution in this problem? That would be found by putting this equal to 0 and then asking what happens to this stationary distribution. What should we expect as a stationary distribution? The Maxwellian. I should expect the Maxwellian once again, right? Because I should expect that limit t tends to infinity p of vt v naught should be equal to p equilibrium of v naught v. The memory of the initial condition should be erased, and you should have the equilibrium distribution again if this process is a stationary random process. So let us see if that happens. Well, the stationary distribution is now does not have any t dependence, so I write ordinary derivatives with respect to v, and it must be, this quantity must be equal to 0. Of course gamma is a constant, so let us get rid of that, and then it says d over d v of gamma goes away, k Boltzmann T over m dp equilibrium over dv plus v times p equilibrium equal to 0. That is the equation that I have, right. If it exists, then it should be normalized to unity and so on. So what does it say? It says this quantity in the bracket should be a constant independent of v. So erase this and write this. I want this P equilibrium to be a normalizable distribution. So P equilibrium must vanish as mod V tends to infinity. That is a necessary condition, otherwise it is not normalizable. You are going to integrate minus infinity to infinity, so the function had better vanish at the end point sufficiently rapidly. I want all moments of this also to be finite. I want the mean square, for example, to be finite. I want it to be equal to kt over m, right. So you want this also to go to 0. You want this quantity to go to 0 at infinity faster than any power of v, because you want all these moments to be finite. Therefore its derivative also will go to 0 faster than any power of v. The value of the constant therefore is 0, because it is independent of v, and when v is plus tends towards infinity the value is 0, therefore it is the value everywhere. Okay. Is that clear? Yeah. Okay. So this constant is 0. But there is another way to write this down, to look at it. You know, if you write this Fokker-Planck equation down, you can also write it like a continuity equation. You can write delta p over delta t plus delta j over delta v equal to 0. This is del dot j in one dimension, with v being the independent variable. And what is j? It is just this fellow, but without the equilibrium, time dependent, with the time dependent density. That is the current. This j is the probability current. You do not want this current to be finite at infinity. You do not want any flux at infinity of probability. So this guy must be 0 at infinity. But in the case of the stationary distribution, it is 0 everywhere for all values of v, because it has got to be a constant.
So in that case, will it always be 0?
Pardon me?
In that case scenario,
yeah,
at infinity the flux
yes,
is
the boundary condition at infinity will be such that this quantity delta kt over m delta p over delta v plus v times p, where this is time dependent, the conditional density, this will tend to 0 as v tends to infinity, mod v tends to infinity.
It appears that in every problem it will become 0.
Not necessarily, we are going to do finite problems where this may not be 0. Okay. For instance, if I had not a velocity but it is a diffusing particle, say, and on one side I have a barrier where if it hits that barrier it bounces back and forth, and on the other side I have a barrier where it absorbs like a sponge, for instance, then this boundary condition on the right hand side is not true if it is an absorbing barrier. It is only saying the flux is 0. So it is equivalent to saying that there is a reflecting boundary condition, but here it is at infinity. So this is a natural boundary condition, that this whole thing vanishes at infinity, otherwise you do not even have a normalizable density. Okay. So I used a physical argument to say that I want this equilibrium distribution to have finite moments. In particular I want a finite variance so that I can relate it to the average kinetic energy and so on. Okay. So this thing immediately tells me if I solve this equation, it is an ordinary first order differential equation. Of course, it immediately says mv over k Boltzmann T times this is 0, and that of course automatically implies that P equilibrium apart from a normalization constant is e to the minus mv squared over 2k Boltzmann T. All I have to do is to integrate this, move it to the right hand side, separate variables, and that is it. Okay. And that is your Maxwellian distribution back again. So, we now know that this equation, this Fokker-Planck equation is consistent with the equilibrium distribution, the Maxwellian distribution. Okay. Can we write a solution of this equation down, a time dependent solution which satisfies this initial condition? What key input would you need for that? We should be able to solve this equation, that is one thing, but it is a hard equation to solve, at least it is not a trivial equation to solve, and you have to integrate this second order partial differential equation. It is first order in time, second order in space, and so on and so forth. We could do the following, we could ask what is the mean square value, the mean value etc. for a given initial condition, which we derive from the Langevin equation, but the question is, can we do it directly from the Fokker-Planck equation? Yes, we can. Yes, we indeed can. Suppose I multiply both sides by V and integrate, then this is the rate of change of the mean value of V, and that satisfies an ordinary differential equation, because if I integrate, I multiply by V, all I have to do is to integrate by parts to bring these derivatives out of this P and write it as some averages. So, you can get an equation for V average bar, V squared average bar by multiplying by V squared, and ask, can those be, do they form a closed set of equations or not? In this case they do, and you can solve them. So, you would have the variance and the mean, the conditional variance and the mean. And then what else would be needed? What assumption would you need to say that that is sufficient? What kind of process would it, continuous process are you familiar with, in which a knowledge of the variance and the mean is sufficient to write everything? A Gaussian, yeah. If this were Gaussian, that would be it, all higher cumulants are gone. And then we could write the solution down explicitly, yeah.
Isn't it just the fact that there is a correspondence between the Langevin equation and the Fokker-Planck equation, and we already used the fact that V naught is Maxwellian in the Langevin equation.
That's right.
So isn't just the reflection of that coming back in the...
Yes, absolutely. So this should be consistent, otherwise I would be very surprised. But we haven't yet said that this is the solution of this, we haven't said is a Gaussian. That is not so obvious as yet. If it were, then this would be immediately true. I could write the solution down explicitly. All I need to know is what does the variance do and what does the mean do, and I can write this down immediately, provided it were a Gaussian, because I know how to write a Gaussian down once you give me the mean and the variance. In fact, let us go back there and ask what is the variance of this guy. What does the variance look like? So, we need to compute, we go right back at this stage and say we have an expression for V squared, we got an expression for V average, let us see what the conditional variance looks like. So, that is a good exercise to do. We have V of t bar is V naught e to the minus gamma t, and we have V squared of t average equal to V naught squared e to the minus 2 gamma t plus gamma over 2 m squared gamma 1 minus e to the minus 2 gamma t. This fashion. That was what V squared is. So, the variance V of t, so let us say for given V naught, we should always remember that this is with a conditional ensemble, then given V naught, this is equal to this fellow minus this squared. So, this cancels out and you end up with gamma over 2 m squared gamma 1 minus e to the minus 2. Notice that V naught is gone. There is no dependence on V naught at all. Whatever be the initial V naught, some given V naught, the variance of the velocity does not reflect it at all, it is gone. And now if you put in the fluctuation dissipation relation which just says the system remains in equilibrium, then this fellow here is kT, k Boltzmann T over m 1 minus e to the minus 2 gamma t. If I now assert without proof at the moment that the solution to this with this initial condition is a Gaussian, if the solution is a Gaussian, is a Gaussian, then we can write it down. P of v t v naught must be equal to e to the power minus v of t bar squared over twice the variance, whatever it is, divided by times the normalization factor. Times this guy, right? You can explicitly write it down. Well, let us put those factors in and see what it is. So it looks big, but it is actually very straightforward. P of v t v naught equal to, now the variance is given to you, it is this guy here. So it is 1 over root 2 pi sigma squared, and sigma squared is here. So it is equal to m over 2 pi k Boltzmann t 1 minus e to the minus 2 gamma t, this guy here, and the whole thing is to the power a half 1 over square root of 2 pi sigma squared, and then e to the power exponent minus x minus v minus v naught e to the minus gamma t, that is the mean squared, divided by 2 sigma squared, and that is minus m, and then there is a 2 sigma squared is 2 kt 1 minus e to the minus 2 gamma t. Looks complicated, but it is actually very simple in structure. Okay. Again, you have to check that as t tends to infinity, it goes to the Maxwellian, the right Maxwellian, and indeed it does, because as t tends to infinity, this goes away, the exponent, that goes away, this goes away, and you have mv squared over 2 kt, which is precisely the Maxwellian, as it should be. What happens as t goes to 0? It becomes singular, you got to be very careful taking limits. It becomes singular because this becomes, this t goes to 0, this factor goes away, you have e to the v minus v naught whole squared, and then this fellow here vanishes. So intuitively it is clear that the only contribution will come from v equal to v naught, so that the numerator also vanishes, and it should in fact go to the delta function. So it starts as a singular, not square integrable or anything, it is a singular delta function distribution, and then becomes a Gaussian. So in pictures what it does is the following. If I plot v here, then initially it is a spike at v equal to v naught, a delta function spike, and asymptotically it is a Gaussian, the equilibrium distribution in velocity, and as time increases, the mean value, which is also the peak in this case, shifts gradually to the left like v naught e to the minus gamma t. So after a little bit of time it looks like this, and then this peak shifts, it comes down, so that the area under the curve remains 1 always, and it finally settles at the Maxwellian distribution, which is just what you would expect this thing would do. we need to prove, of course, that the solution is a Gaussian. That takes a little bit of doing, but it is not very hard in this context. We can actually compute the other cumulants and discover that they are all 0, and then it is exactly this. There are other ways of solving this, and we will not do that right now. We will I'll come back, and if time permits, we will talk about other ways of solving this equation. Okay. Because I want to also introduce another stochastic equation for the position of a harmonically bound particle, which would look exactly like this. And we know all about the harmonic oscillators, so we can use that knowledge to solve this equation. But you can see physically this is happening. Okay. What is remaining in this context is to ask, what does the velocity correlation itself do? What does the correlation of the velocity do? And then there are several questions that arise, which we will all answer successively, namely, what about the position of the particle? We made this model, we solved the equation of motion, we found V of t, we found its average distribution and so on. What about the position? And then a much deeper question, should we not really look at this particle in phase space, namely both x and v together? And then should we not write down a stochastic differential equation for this quantity and then find this distribution or conditional density in phase space for both position and velocity together? That is really what we should do, because then we could put external forces on the particle and write the correct Langevin equation down and solve it in phase space, because dynamics happens in phase space. So we will do that, we will write that. That will mean a multi-dimensional, two-dimensional Fokker-Planck equation, but we can do that without much difficulty, and you will see how the physics goes in. Just one remark here, and that is to find the following quantity. We found already v squared of t. Let us do v of t prime and find the average here, where t and t prime are both positive numbers but different numbers. I leave this as an exercise to you, because you would have exactly the same thing as before. Again, each of these is v naught e to the minus gamma t, etc. So there is going to be a v naught squared e to the minus 2 minus gamma t plus t prime. Those would be the first terms. Then there would be one term where you have a v naught term multiplying an eta, eta of t2 say, and then a v naught multiplying eta of t1. Those averages go away, and then you are left with plus gamma over m squared integral 0 to t dt1 0 to t prime dt2 this fashion e to the minus gamma t minus t1 minus gamma t prime minus t2 in this case times eta of t1 eta of t2 average. That is a delta function. So you have a delta function. Now you got to be careful, okay. So this much is straightforward, but now in removing this delta function to do the integral, you have to be a little careful. So let us, for example, see in pictures what happens. Here is t1, here is t2, this fellow is integrated up to t, the other guy is integrated up to t prime. Let us suppose t prime is smaller than t. We also have to look at the case where it is larger, but this whole thing is completely symmetrical in t1 and t2. So we could actually interchange after we find the result. So let us suppose this is t prime, and what is the constraint on the integration? The delta function. And where does that fire? On a line which is at 45 degrees. So it clearly fires on this line. This is the line t1 equal to t2. This is the case t greater than t prime. Otherwise the rectangle is upwards. Now what does that tell you? It says that you are going to fix a t1 and scan t2. So you fix a t1 and you scan in t2 in this fashion, and of course you hit this delta function. You fix the next t1 and scan, you hit the delta function. And you can do this till t1 hits t prime, and after that you get 0 is the answer. So the integration is gets cut off at this point here. So this thing reduces to integral 0 to t prime dt1 e to the minus gamma t minus t1 minus gamma t prime minus t1 once again. You can set t1 equal to t2 inside the integrand by using the delta function constraint, but the t1 integration is constrained to stop at t prime, okay, and then you have to do this integral, etc., etc. If t were greater than t prime, do the t2 integration later, do the t1 first. Not surprisingly, what answer would you expect finally of this? What kind of function of t and t prime would you expect? I would expect it to be symmetric under t goes t and t prime getting exchanged with each other, right. But we also know that if it is a stationary process, I would expect this to be a function of the time difference, and I want it to be symmetric. So what would you expect? You would expect mod t minus t prime. I would expect the answer to be mod t minus t prime. So show that this fellow reduces to e to the minus gamma times mod t minus t prime. It suffices to do it for t greater than t prime and then use this symmetry out here. And you will see therefore that the velocity is exponentially correlated. Okay. Then there is a very powerful theorem which says there is only one process which is Gaussian, which is a continuous process, which is a one dimensional process, which is Gaussian, stationary and Markov and exponentially correlated, and that is this process, there is nothing else, and various other processes can be reduced to it by changes of variables, reparameterization and so on. So that is the reason why this is worth studying in such great detail in addition to this particular example here. Okay. So we will take it up from this point, and I will point out how we can extend this to phase space and see what exactly where the diffusion approximation comes and so on. We have got to understand the role of this gamma a little harder, a little better, we'll do that. Okay, so we will take that up on Monday.